Like I'm sure half the people have reasons why they can't, but other half do. Turn on video. Can you all see my screen?
Yeah.
Okay, so as you can see from this, my handwriting is terrible, so you'll have to bear with it. If something's unreadable or something, tell me, I'll tell you what it says. Okay, sad one person only. One is better than zero. Okay, anyway, so fairy sequences. They're really nothing fancy, although they're magical, of course, because they are fairies. So essentially, in fact, this began a couple of centuries ago when there was this simple question asked: how many fractions can you have of distinct values, all less of the form, say, a by b, such that their value is less than 1, their values are all distinct, and the denominator is less than 100. Does anyone know how we would do this? Okay, first of all, how many fractions exist with denominator less than 100?
Infinite.
Hmm?
Can some of them be same?
They have to have distinct values, but for now, ignore that fact. Assume you're allowed to have same value.
I guess 1 plus 2 plus 1 till 99. So some more question.
Yes, 1 plus 2 plus stuff until 99. Okay, nice. So what happens when, like obviously this happens when, suppose you fix a value of b to be say 7, then you can take 6 values for the numerator. But now you're not allowed to repeat values. So now how would you do this? For each denominator, you only want to choose a value such that this fraction has not come earlier.
So we pick the ones which are like not reducible. So for prime there are I guess 6, and for normal n there are 5 of n.
Yes, the answer is exactly that. Phi of 1 plus phi of 2, and so on until phi of 99. So like some guy did this. Apparently the out of the 3 solutions they gave in the magazine, in fact 2 were wrong. So people could not do this. So you are cleverer than people from 2 centuries ago or something. Okay, anyway, so suppose we have a number line. So now there is a guy named John Ferry who, Farey, his name was not Ferry, who decided to put the numbers on the number line. Say we have a 0 and a 1. Now for 2 we add a half here. Then we have a 1 by 3, and we have 2 by 3 somewhere here. This is slightly inaccurate. We'll ignore stuff for now. Then you have a 1 by 4, 1 by 2 again, and then a 3 by 4. And then he kept adding stuff. And then he found some interesting properties that looked true. And he actually wrote this in a letter to Cauchy, who proved it. And it's why, and he credited fairy, which is why they're called fairy sequences, in fact. So, okay, what observations did he make? Suppose we fix two numbers, say 1 by 3 and 1 by 2. Or in fact, let's just look at two adjacent numbers, okay? So these numbers that are here so far have denominator at most 4. So this is called F4, or the fairy sequence of order 4. F5, you just add 1 by 5, 2 by 5 and stuff to this. So now what property can you observe? Maybe it's not that obvious directly from this, but you'll see. So consider two adjacent terms, say 1 by 5 and 1 by 4. Then we have a 1 by 4, 1 by 3. Then say 2 by 5, 1 by 2. So he observed that if you take the cross product of, I mean, like in this example, let's say 5 into 1 minus 2 into 2. This is always equal to 1. For example, you can look at this 1 by 3 and 2 by 5. 5 into 1 minus 3 into 2 is, or mod of this is 1, depending on which order you're taking this difference of. So he actually discovered this property, and this is in fact true. We'll prove it later. But first, some other observations that he made. Let's remove this. So say we pick the numbers 2 by 3 and 3 by 4. Which is the smallest fraction that is going to have a value between this? I mean, in between this. And by smallest, I mean which has the smallest value of b. This is like 0.6.
12. Like B will have smallest 12.
Half?
Hmm, what? No. Like it has to
Actually,
have,
not half. Sorry, not half.
yeah, it should be between
7.
0.6. Yes, 7. So that is true. How did you get 7? Like, do you know?
4 and 5 doesn't work, so
Yeah.
and 6 also doesn't work, so 7 works.
Yes. In general, or actually, let's see if you can find the pattern. Let's pick, say, 1 by 4 and 1 by 3.
I
What's,
think you sum the denominators or something.
yes, exactly. Or, okay, we said not adjacent. So, in general, the number that is going to come between, say, a by b and c by d. Also, are you only summing the denominator? What about the numerator?
Yeah, that too.
Yes, so it in fact becomes a plus c by b plus d is the first number that is going to come between the fractions a by b and c by d. We will also prove this. Okay, so first of all, do you people see why? Okay, first of all, some terminology. We say two numbers, my handwriting. We say a by b, what is this? And c by d are fairy neighbors if the value of ad minus bc is 1 or minus 1. Okay, and like we observed that this was true. In all these cases, this cross product is equal to exactly 1 or minus 1. Okay, right. So first of all, we guessed that this number a plus c by b plus d that comes between two fairy neighbors a by b and c by d is the smallest one. But why is this even, why does this appear in the fairy sequence? As in, why do a plus c and b plus d have to be coprime? If they were not coprime, this would not be in the fairy sequence. We're only counting things which are irreducible. So think for a while if you want, why can't GCD of a plus c and b plus d be not 1?
Otherwise, AD minus BC could not be 1.
Yes, exactly. Could you elaborate?
Like if you assume they both of them are divisible by D, then AD minus BC, AD would be congruent to BC mod D, meaning AD minus BC is divisible by D. Oh,
Yes,
sorry, I used variable D. You
it's
can use
close.
P.
Yeah, I'll use p. So suppose a p divides b plus d and p divides a plus c. Then d is minus b, so this becomes minus ab. Minus bc, c is just minus a, so this becomes plus ab. So this becomes a 0 mod p, but this value is actually equal to 1. So this prime cannot have existed. And therefore the GCD is in fact 1. Okay, so now let's prove these properties. First, we'll show that fairy neighbors always have to have this AD minus BC equal to 1 property. Lines. So, does anyone know how we would try and do this? Like also like in general, it's fine even if you think your idea is silly, might not work. You can just speak. Not everyone gets it right in the first try.
Can you give us a minute to think about it?
Yeah.
Most probably, we have to find
Uh,
another fairy
cons-
number between them if it is not one.
yeah, take the value 1 and consider P by Q between them, and it will come up to A plus C by B by D.
Yes, that is an
And
interesting.
that will
Let's
form
actually
a
just
series
try.
sequence.
This is actually not the proof I know of, but things are simple enough to have various proofs. So let's try this. Is the next adjacent fairy after A by B? Okay, so fairy sequences are defined by the order of the fairy sequence. That's why we say Fn. N is the maximum denominator you are going to have. So if the order was B, then yes, the first thing after it would be A plus 1 by B, probably. Or actually, maybe not even then. But in general, what we are. Okay, it's not. Fine. Okay, right. So let's suppose this is true. We'll first show this direction that if AD minus BC minus AD is equal to 1, then you can't have a fraction below it such that Q is less than max of B and D. So we have BP minus AQ. Okay, I'll just give me a minute. I'll be back. You people can think about this. Yes, exactly. That works. So what he is saying is 1 by BD is this difference between the fractions because of our assumption that BC minus AD is equal to 1. But now we can write this as C by D minus B by Q plus P by Q minus A by B. But this thing, this denominator which is QC minus PD, it has to be positive because that's what we have assumed. CD is greater than PQ. So this thing is at least 1 over PQ or DQ. And this thing is at least 1 over BQ. So we indeed get this. Cross multiplying, we get that Q is at least B plus D. Makes sense. Does anyone have any questions? Why does AQ minus BP being equal to that imply that? Oh, okay, fine. Yes, you're right. Fine. Wait. Why are those two things equal?
AQ minus BP, they both are equal to 1 only if they are in pairing.
Oh, we haven't shown that yet, right? Like
Like
we're
it,
showing first that. Go on.
like 1 or minus 1, no? So you cannot directly assume equal, I guess.
Oh, you can assume it's 1. Like the bigger thing. In
Ah,
this
yeah,
case, BP minus AQ.
yeah.
It has to be 1. Yes, like we're assuming that A by B and C by D are Fairy neighbors, as in BC minus AD is equal to 1. And we're showing that nothing can come in between them. Next, we will show that if you have two adjacent things in Fairy, then B by D, BC minus AD is in fact 1. Yes, so now that we're done with this part, I'm assuming no one has any questions because no one has asked anything. So now we'll do the other part. Suppose we have A by B and C by D are Fairy neighbors. Can we prove that BC minus AD must be 1? I'll give you a minute, think about it.
Do we do this by induction?
Yes, induction works perfectly well. So suppose the base case is just true because you just have 0, 1, 1 by 2. You can check it's true. So now suppose it's true until n, and we have to show it's true for n plus 1. So suppose we have, say, x by n plus 1 uh, greater than a by b less than c by d. So like earlier, a by b and c by d were Fairy neighbors. So we know that bc minus ad is equal to 1. And in fact, we can use essentially the same thing as the previous proof to show that n plus 1 is at least b plus d. But fine, that's already been done. So can we show that also n plus 1 is in fact equal to b plus d? Okay, let me just phrase it like this. From the previous proof, we have that n plus 1 is at least b plus d. So in fact, if we had a fraction that has b plus d as a denominator, then we would be happy.
What are we trying to prove?
That a into n plus 1 minus bx is minus 1.
But it might happen that between a by b and c by d there are more numbers of the form x by n plus 1.
Can that really happen? Okay, let's prove that that can't happen. Suppose you instead have also an x plus 1 by n plus 1 over here. Or maybe it's actually not that obvious. Why? If you just go with the normal proof, we will see why. So suppose x by n plus 1 is one such fraction with the denominator n plus 1 in this range. We'll show that it's the only one. Okay, so n plus 1 is the smallest denominator that appears between a by b and c plus c by d. And we know that n by n plus 1 is at least b plus d. So from earlier, which I unfortunately somewhat spoiled, we have that a plus c by b plus d is going to be a number between in this range, right? So we have a by b. Okay, also why is this true? Can someone just prove this? Why does this inequality even hold?
Just cross multiply and
Yes, exactly. Just cross multiply. This becomes bc minus ad, which is positive because a by b less than c by d. So we know that for n plus 1 equal to b plus d, there does appear a new number here. But earlier it was not there. So in fact, n plus 1 is equal to b plus d. And we know a plus c, this exists. So suppose we also had, let's say, okay, also we can verify the cross product rule still holds here. A plus c into b minus a into b plus d is just equal to bc minus ad, which is still 1. So what Arjun asked, why can't we have two numbers here? So let's say a plus c plus 1 by b plus d also existed. Yes, it does. Anyone see a problem with this? Think for a while.
Yeah, it cannot be less than c by d.
Why?
yeah, just
Yes. Yeah, if you cross multiply, you just get VC plus DC greater than AD. But this is just saying D is less than 1, which is not possible. So in fact, this cannot happen. And if it was A plus C minus 1, you do a similar argument, but for it can't be greater than A by AB in that case. So what we have proven, I'll just summarize. So first, just the Farey sequence definition is just the Fn is the Farey sequence of order n, which contains every reduced fraction with the denominator at most n in 0, 1. If two numbers a by b and c by d exist such that bc minus ad equal to 1, or that they are Farey neighbors, then the smallest n for which Fn contains a number between them is b plus d, and this number is a plus c by b plus d. And we've proven this stuff. Okay, so now a somewhat related thing, but it is quite interesting. So this is called the Stern-Brocade tree. It essentially says start with 0 by 1 and a 1 by 0. Ignore the fact that 1 by 0 is undefined, etc. Now each time, if you have two numbers a by b and c by d, Write the number a plus c by a plus c divided by b plus d, like in between them. Just add numerators and denominators. So in this case, that becomes 1 by 1. Next, this becomes 1 by 2, 2 by 1. And you just keep repeating this. Now we actually claim that every single rational number appears in this tree. Okay, it's not really obvious why this is a tree. I'll probably just write it better. Technically, these are above. You get the point. Okay, so first of all, we don't really care about this part. It's just reciprocals of what you're going to get over here. And you can see that, right? I'll assume you can indeed see that.
Yeah.
So
I
essentially,
didn't exactly get how the tree structure is there.
it's essentially, wait, let me get a diagram of this thing. Yes. Yeah, this is why it's called the Sternberg tree. Each number that you see, like if you look at just the two things adjacent closest to it, in this case, this and this, 3 by 5 is in between them. So it has 1 plus 2 by 2 plus 3. So like I sort of drew it badly, but this is why it's the tree. A stern ST.
But like all these numbers in this are not fairy numbers, right?
Hmm.
Like 2 by 1 cannot be.
Yeah,
It's
so it's
negative.
essentially fairy numbers and their reciprocals.
Fine.
So essentially this right half of the tree, this entire thing, is just reciprocals of this side. Because like 0 by 1, 1 by 0. You get the same thing but ulta. So I'll move this a bit. So it's in fact really saying you start with 0 by 0 and 1 by 1. Also, I'll just define this. If you have a by b and c by d, their mediant is a plus c by b plus d. It's median with a t. Kind of like inversion. Yeah, I guess. Product is 1. So like sort of radius is 1. You have
Yeah.
that thing. So a plus c by b plus d is their median. Is this. So really this theorem, this Sternberg tree thing is saying you start with 0 by 0. It's not really, it's somewhat a stretch to call it related to inversion, but like he meant, if you look at the distribution of these values, this is like 0 to 1, and then you have 1 to infinity. Like essentially, if you imagine inversion, also like if you have the circle, like the points in this range are getting thrown to the points in this range. So I assume that's what he meant.
Yeah.
Yeah. But no, it's not really relevant to the tree. Yeah, so this is saying
How are the points in one range getting thrown to the other?
in inversion, that's what happens, right?
Like in the tree.
Oh, I mean the values. Like over here, the values on this side are in between 0, 1, and the values on this side go 1 to infinity. It's a bad analogy, but fine. So this thing says that if you have two numbers, each time I mean, not replace, add their median in between them. 0 by 1. So in this case, 1 by 2. Uh, Why is there an Yeah, I get what you mean, but why is there an interval which doesn't have any numbers? Like it could just somehow magically skip exactly one number and cover everything else. But yeah, I agree. That does sound like a natural thing. Then the interval. I mean, how are you defining two rational numbers closest to it? You can have many, right? Endpoint. Like suppose I ask why is 2 by 5 in this tree. What are the endpoints you're taking? No, no, it's fine. Okay, so like think about this for a while. We have to show that every single rational number between 0 and 1 appears in this tree.
Could you one show the tree again? Yeah.
Is it like for every denominator, the number which is co-prime to it comes in the numerator? Like, wait, is it proof that all the fairy numbers come in this tree? Do we know that?
Fairy numbers are all rational numbers in 0, 1, right?
Yeah, fine.
Yeah, okay.
Yeah, I
Keep
think if
going.
we like project this onto the one line, then this will just become the fairy sequence. Like if we look at it in one go.
Hmm. In one go, yes, but individually, I'm not sure how much that helps because in fairy, first you add everything with denominator 1, then 2, then 3, then 4. But here, that's not really true. Like, look here. For example, 4 and 5 get added, then 5, 7, 8 all get added, and not all of them get added at the same time. But yeah, essentially every fairy number is appearing. I'll leave this here.
Is it like then using induction, like you prove for n, then if the denominator is n plus 1, then it needs all the the denominator of like a by b and c by d, b and d both should be less than equal to n. So seems to be induction.
Yes, induction does indeed work. I'm myself not sure of exactly how it will work, but it will work. So let's try and figure it out. So suppose everything until denominator n has appeared. And now we really need to look at a denominator of n plus 1. So suppose we have this number x by n plus 1. I seem to be using the same thing a lot. I think before this you would need another fact. Yeah, okay. Let's actually look at how this stern Broca tree looks after each minute. Suppose every minute you do this median thing, how they look. So we have 0, 1, 1 by 2. That's a very similar property to what held in the fairy sequence, and it's in fact a direct consequence of that. That also holds. This cross product of adjacent things is still going to be 1. Does anyone see why this is true?
Yeah.
Yeah, because a plus c by b plus t we've shown earlier. It is in fact the first number that appears in between them, and therefore, and also, I think I just may have been wrong earlier. You can probably just use fairy stuff, yes. Because essentially what you have is you don't really care about the order in which this tree happens. You can just focus on some interval. And you're just essentially adding the median repeatedly. And you want to show that it eventually will reach this number. So I think this will just in fact work. Okay, so suppose we want a number a by b to appear in this sequence. Also, we'll just come back to the, or actually fine, we'll just try the induction proof. So if you want this number to appear, you want it to be between x by y and a minus x by b minus y, such that these things are fairy neighbors. Do you see why this would finish? We're inducting, so we're assuming it's true for all numbers below b, the denominator.
Yeah.
Yeah, because then this numbers x by y and a minus x by b minus y are neighbors in this tree.
Could
Now,
you repeat like what's the claim you're exactly making here?
no, I'm trying to show that a by b appears. I'm inducting on this value of b. So if we want it to appear, we want x by y and a minus x by b minus y to be there. That's when this gets added, right?
But if they are not adjacent, then
Yes, exactly. So we need another condition that a minus x into y minus x into b minus y is equal to 1. This is the condition for being neighboring that we just showed.
no. But like even if this is true, it still might happen. They are not neighbor.
Why?
Like originally 1 by 0 and 0 by 1,
Huh.
they satisfy this condition, but they are not neighbors, right?
Oh, they are initially neighbors, right? Like the top of this. Well, yes, they are the first neighbors.
Um, but why will all such pairs be neighbors?
Hmm. Oh, that we are inducting on, right? So we are showing that essentially like every number of the fairy sequence appears in this. Somewhat.
Could you tell the exact claim? What's the claim that you are claiming that all numbers appear, or like
Yeah,
any
I'm
two numbers
saying that.
satisfying this property will be adjacent sometime?
Oh, that also. Essentially, I'm saying you can just think of it as the fairy sequence and you're repeatedly adding the mediant in between them. It's like I'm saying x by y and a minus x by b minus y were neighbors before this. Also, like because y and b minus y are less than b, this holds by induction. So you're right, fine. We strengthen the induction hypothesis to like first all appear, And second, that a neighbors if and only if BC minus AD is 1. Also, neighbors, I'm not looking at it in the tree sense. I'm instead thinking of it as look at an interval and just keep adding numbers in between. So, for example, these two are neighbors at this point. Like basically, I'm claiming if you have at any point you look at these numbers that exist, any two neighbors satisfy this. And if they satisfy this, they must be neighbors. Did you get that? Did I explain it badly?
Yeah.
Okay. So we want this to be true. Okay, and this is just saying we want ay minus bx equal to 1. So given an a and b, you want to find an x and y such that ay minus bx is equal to 1.
Like, can't we just get it this result directly from the median thing, because you already showed that between a by b and c by d with bc minus ad1, the number with smallest possible denominator between them is a plus c by b plus d. So this means we never miss any denominator, right, in a particular interval.
Yes, okay, fine. That's just much simpler. But fine. Yeah, that works. Ignore this somewhat overcomplicated thing, but what I was going for is by, say, Euclid's algorithm, we can find an x and y such that this is true. But fine, yours is just
What
clean.
was Arjun's proof?
No, like literally do the exact same thing as fairy. It's essentially equivalent to fairy. Between a by b and c by d, the first thing that appears is a plus c by b plus d.
Yeah.
So in fact, we directly have this stuff.
Yeah, fine.
Okay, cool. So now, like a bunch of people decided, why do we have to start with 0 and infinity? What happens if we just start with two random numbers, say a by b and c by d? Or actually, it probably gets boring after some theory. So let's do a problem just to see like fairy is not just some random thing I'm ranting about. It actually is useful in Olympiads. So I'll get a problem. We'll start with a simple one. Yes, this is the problem. It came in like Vietnam National Olympiad 2030, problem 4.
Do you like you write the sum, so you introduce the denominator also, and it looks like a fail thing.
It in fact is very similar to this tree that we looked at. Let's just solve part A first. How are you introducing these denominators?
So like one by one. I mean, there are two ideas about which I'm not sure which works. One by one and thousand by one. Another is one by and like it appears in the form of a by b where a is one. So pick the b in the fairy sequence.
Are you sure this exactly works?
Ah,
Because
that gives that will be cancelled out, right? If there are 2013. Yeah, I mean
the
it should be
problem is
co-prime.
in this earlier thing of this tree that we looked at, all neighbors had cross product equal to 1.
Yeah, fine.
But in this case, that's not true. So like, yes, we want 1 and 1000 as numerators. So essentially we want to choose denominators, as Pranav said, to like make these numerators look like what the problem asks for. Why would we choose 2013 as denominator? We want 2013 to be in the numerator. So like, there's 2013 that's here. The point of this 1 and 1000 is so that if we do this turn Brocade tree stuff, then the numbers that are going to come, essentially you're just doing exactly what this process is.
I think you can start with 1 by 1 and 1000 by 1001.
Yes.
And basically all the
And 1000.
denominators and
Yes.
numerators would be co-prime throughout. So we only
Yes.
have to look at.
Exactly. So that's right. So we just start with 1000 and 1000 divided by 1001. And now this is essentially the exact same tree as before, except we started a bit late. Instead of starting with 0 and going all the way to 1, we instead start with 1000 by 1001. And in fact, the exact same result as before holds. That every number appears in this. And as Arjun said, all these numbers that are going to be formed are irreducible because these things are coprime initially. So we really care about how many times we can have the numerator 2013 in this range.
But it is also given that we want 2013 only after 2013 transformations.
Yes.
So isn't that a problem?
Think. Would it be a problem? Yeah, it is a valid point. If this 2013 was replaced with some 100 or something, the method would not have worked.
But like after any transformation, the numbers which were already there are not erased, right? So how does it matter?
No, his point is suppose use 2013. Yes, indeed, we can use that. Yes, so the Arjun's point is suppose you're doing this operation and stuff.
Yeah, I got it now.
Okay, anyway, to Pranav, the problem is suppose if we replaced with 100. If you do this operation only 100 times, maybe that's a 2013 that's going to come later in this tree, but it does not appear now. But as Bora says, we use 2013 greater than or equal to 2013, which is essentially saying each time the new number that comes, it's increasing by at least 1. So after 2013 times, everything that is formed after this will have like numerator at least 2014. So we really don't care about that. So we only want how many times 2013 can appear in this range. And this is easy. Can
Yeah, I
anyone?
think we just have to do some computation now.
Yes.
So should we move to the next problem?
Oh, I assumed someone wanted to do the computation. But fine. Computation no one likes. This can be 2014 or 2015, I think.
No, but computation, what do you do? Like, in what sense?
Oh, just
You
find
just
how
cross
many
multiply.
x satisfy. Yeah,
Okay.
just how many x satisfy this. Only two. Okay, can we solve part B also? It's rather similar.
So I think you do like 1 by 2, 2 by 3, 3 by 4, and so on.
Yes.
Uh, Also, is there any easy way to solve this question without fairy?
There probably is. I haven't really looked at the official solution.
Okay.
For part A bash, you don't really know if every single instance of 2013 appearing works, right? Also, like, why do you want to do 2013 times? Like, that does not sound very nice. Yeah, so as Arjun said, the exact same thing here. We just want pick 1 by 2, 2 by 3, 3 by 4, 4 by... Actually, how are you choosing these denominators?
Could you repeat?
How are you choosing the denominator?
Like I'm
Oh,
just
you can just
trying
do
to
5. Okay.
preserve that AB minus CD equal 1 in the
Yes.
simplest possible way.
Yeah, okay, that's actually a simpler way. But yes, this works. Just go 5 by 6 until whatever. 1000
Oh,
by...
you just do 1 by 1, 2 by 1, and so
Yes,
on. Oh,
that is simpler, yeah. Just look at 1 by 1, 2 by 1, 3 by 1. And by what we did earlier, each neighbors have cross product 1. So we have that 2013 by x in this range 1 to 1000 will work. And again, just you can do the computation if you want. I don't remember the answer for this. It's irrelevant. Okay, so now we can do another problem. I think some of you might have seen this and like may know other solutions, but the fairy solution is also quite slick. Yes, USAMO 2020. And very similar to NMO P1 this year, but bad memories. Ah yes, USOM. It was online. Okay, so like specifically for this solution, there are a lot of ways. That's like one you can do it geometrically, one like just induction.
Do you take the numbers A1 by B1, A2 by B2, so on? And like, this term is of the fairy thing, like AIBJ minus AJBI.
Yes, that in fact is very close to working. But there is a slight problem.
yeah. So you first W log assume that they are in that increasing order.
No, that's not the only problem.
They're not.
So they
Oh,
can
they
be
can be
0.
0.
Yes, 0, 1, 1, 0, 0, 0 exist.
But in our in our that tree we allowed 1 by 0, so that shouldn't be a big problem, right?
Yeah,
But
but
what if you have like 3 by 0 or something as well?
and also I think 0 by 1 was the problem. Okay, there's a very simple fix to this though.
Do you just like manually manage the zero cases? I guess.
I guess you could do that. But judging from the comments on the thread, people did not succeed in manually doing this.
I see.
But there's actually a very simple change you can make instead of looking at AI by BI, which just gets rid of the 0 being in denominator case.
BI by A?
What if AI is 0?
I mean, like, both are zero, then it's trivial. It's like you can
No, I
just
mean, what if it's 0 for 1, and what if 1 comma 0 is there and 0 comma 1 is there? Then either way you're ending up with a problem.
But in a tree we allowed 1 by 0, right?
Hmm. Okay,
So
also, what is the proof that you're going to do? Assume they are fairy. Assume A1 less than B1. Fine, let's actually leave it at this. And I mean, let's not bother trying the optimization until we see why this fails. So as you people said, we know that these are indeed fairy neighbors.
so like I AI by BI comma AJ by BJ satisfy whenever there are odd number of fractions between them, I guess.
Or
Like A1 by B1 and A3 by B3 satisfy, right?
it depends. Yes,
You
okay.
just
Fine.
you just take it to be a fairy sequence, like take A1 as that and wait,
I
are
mean,
the
in the
ordered pairs
fairy
available?
sequence, hmm?
We can choose the ordered pairs, right?
Yes, okay, fine. Maybe you want to find the answer first. But I mean, you also have to determine the largest possible. You have to prove the bound also. Okay, actually, maybe, yeah, fine. We'll look at the answer first, what it's going to be. Suppose we replace 100 with 2.
It's one.
Yes. For 3.
it's 2n minus 3.
Oh, you remember? Or did you figure it out now?
I remember the constant 2 and the minus 3 was not hard to get.
Yeah, okay. Yes, indeed. The answer is 2n minus 3. Do you remember the construction also? Or?
Yeah, I found it like
Oh,
1, 1, 1, 1, 1, 1, 1, and after that 1, 0, and 0, 1.
hmm?
Like 1, comma 1, 1, comma 1, 1, comma 1, so on, and the last
Distinct
two are.
ordered
Distinct
pairs,
order
right?
pairs. Distinct, yeah.
Oh, sorry then.
Yeah, otherwise, in fact, 2n minus 3 is not the answer.
1 comma 2, 2 comma 3, 3 comma 4. So not
Yes, that works. Or in fact, you could look at it as 1 by 2, 2 by 3, 3 by 4, and so on.
yeah.
Yeah, that indeed works.
How does this give 2n minus 3 pairs?
Does it now? Oh, this doesn't. Oh, did you say? Yes, there is an addition to be made. Okay, this almost works, yes. And in fact, the fact that 0 is allowed is important. If it's not allowed, maybe the answer is not 2n minus 3.
What if we took 0 by 1 as the first one?
Yes. Great. Does this really help in this case?
I think instead of 2
No.
by 3, you should take 1 by 3 and so on.
Yes. That way you have a 0, comma 1 works with all of these things.
But this is not a fairy sequence, though.
Close enough. I think some modification of the fairy sequence also work. But yes, this is a construction that works.
I mean, if it was a fairy, then 1 by 2 and 1 by 4 should also have worked, I guess.
Yeah, okay. The main problem in this case is the 0 is allowed. Otherwise, yes, we could do fairy stuff. Like essentially, if you did only fairy stuff, you would expect it to be like n plus something or n minus something, because that's how many adjacent neighbors you have.
You not necessarily need adjacent, no. So, suppose in the original fairy we have numbers 1 by 3 and 1 by 2 were neighbors, and then you introduce 2 by 5 between them,
Mm.
and then 1 by 2 is also there. So these three work, right? Like 1 by 3, 2 by 5, 2 by 5, 1 by 2, 1 by 3, 1 by 2.
Yes,
So like whenever two numbers have an odd number of fractions between them, they work.
always.
Yes, I guess. Like now, wait. Not necessarily odd. Yeah, like you can introduce 3 by 8 also between 1 by 3 and 2 by 5. Then also like even numbers are there and it works.
Yes.
Yeah, so like it's the my point is it's not like n plus something. It's larger than that. Seems to be at least.
No, but
Yes.
like 3 by 8 and 1 by 2 here won't work. So it's not like every pair or something.
Yeah, I think apart from the adjacent things, you can only have a few that work.
I see.
Okay, 1 second, I'll just be back. Sorry, again. Okay, sorry, my parents keep calling.
Okay, so like I'm not sure if this works, but if we take like the first 100th fairy numbers, something near to that we can reach, I guess. I think I have to manually work out once.
First 100 fairy numbers.
I mean, uh, like take the n such that the number of fairy numbers in order n are less than 100. Take the largest such n,
Hmm.
and then you add some more fairy numbers to make the number of numbers in the sequence to be 100, is what I meant.
How do you count how many like pairs, good pairs or whatever you're getting?
Yeah, that's what I was thinking. But like, I think we can manually count and check if it works.
That sounds.
I mean, just to check. I think we
There
can
is an easier way to do this.
using faith.
Yeah, I mean using fairy, I guess. Okay, so just having a sequence of stuff and directly counting doesn't work. So we'll probably just induct. I realize I said we won't induct initially, but I must take it back. So suppose we are inducting, we want to show that when you're putting a new thing, you want what? At most two new things to form.
Yeah.
So in fact, the fairy sequence does work. I take back what I said earlier again. Because in the fairy sequence, every time you're inserting something, you do create two new pairs, like this thing and this thing. But bad example, but fine.
So this means the zero, even if the zero was not there.
Without the zero, the fairy works.
But
But
without the zero, is there any easy construction?
I think there is. Uh, it was just what you said, I think. This works.
No, but like if we exclude the zero.
If you exclude the zero, there is another thing that works. But it's essentially using fairy ideas, and it's in fact the first problem of the problem set I put, kind of. You can choose Fibonacci numbers.
Which problem set were you talking about or something?
The one I'll send after this class. Like, I'm also using some problems from there, so I didn't want to send it out just yet. But yeah, picking Fibonacci numbers also works. And apparently many people actually found this. So, nice. Scary problem sets. No, the problems look fine. Okay, yeah, so what we did in the fairy is every time you're adding something, you create at most two. Can we show this in general? Or it's like something similar to it?
What do we need to show? Like for
Uh,
general.
when you're adding a new number, it creates at most two new pairs.
I think we have to show something else that a particular we can choose a number which is like connected to at most two other.
Yes,
Because in the 0 by 1 thing, the 0 by 1 was relating to a lot of.
a lot. Yeah. So yes, you can't just say it's true for all things. Some things may be connected to more than two things. And this is in fact what the official solution does, I think. Find a thing that has at most two neighbors. But in the spirit of fairy, this is probably not that easy to see, so I'll actually just give it away. Instead, consider AI by AI plus BI. As in like AI comma AI plus BI. We see these fractions.
So what's E and B here?
D. Oh, like from the problem. Instead of taking
Oh,
AI BI, consider AI and AI plus BI. this cross ratio still remains 1. We can check that. So in this case, the cross product, the AI AJ cancels. So the cross product is the same as earlier. So like it's essentially the same thing that you have, but you're just avoiding zeros, essentially.
Also, why do we need it should increase the number of pairs by at most 2?
If it increases by more than 2, you can't really end up, no?
Oh.
Like you have 2 into n minus 1 minus 3. And you want to show 2n minus 3. So you want to show at most 2 get added, right?
So like when we add one more pair at most 2, it is 1, right?
Yes.
Whatever like we add.
Hmm.
Okay.
So now we're actually very close to done. Suppose we added a number. How many new neighbors can it create in most cases?
What do you mean, like?
1.
This new number that you're adding, how many neighbors can it have?
N minus 1 in the best case.
Yes, ignore that annoying case. In general, like what would you want it to be, right?
Like we have to prove it will have at most 2, but
Yeah.
So like suppose.
I didn't get your question.
Oh, so basically my point is you have this essentially on the number line. Every fairy problem, draw number line. It usually works. Suppose these fractions that we have here are like this. Okay. And now we are 5 purple. We add this yellow number here. How many new neighbors can it have?
2.
I think a lot in some cases. Yeah.
How? The 0 thing works because it's the smallest here. I'm adding between 2 things. Like essentially assume that obviously you have at least one pair is non-zero, right? So we'll add that in and see what happens. So how do I define a neighbor? A by B and C by D are neighbors is BC minus AD is equal to 1.
After like suppose 10 or 12 iterations of like fairy numbers, like suppose you're taking the number line with order 12. So
Okay.
0 by wait, 1 by 2 and 2 by 3, they are still the fairy numbers, still neighbors, even though there are many numbers between them.
No, they are neighbors in F until F4. After 5 comes, you have a new number that appears in between.
No, I think, but some numbers can have a lot of neighbors in the fairy sequence only. For example, like, could you just return to the fairy sequence you had drawn? Something. Yeah, so for example, like originally say 1 by 2 and 1 by 1 neighbors. After that, 1 by 2 was neighbor with 3 by 5. So for example, this number 1 by 2 will be a neighbor with a lot of things, right?
Yes. What number would not be a neighbor of much things? What gets added later?
Okay, the corner ones, yeah,
Corner.
or something.
No, the corner ones can have lots of neighbors. Like as we saw in this construction that you gave. The corner one literally has every neighbor. But fine, essentially if you visualize this as a fairy sequence, the ones that get added later are going to have less neighbors. By later, I mean in the fairy sequence, we first add shuffle denominator 1, then 2, then 3, then 4. So consider the number with the maximum denominator here. How many neighbors can it have?
At most 2.
Yes. So delete and induct?
Yeah, we are done.
Yes. Okay,
So
I'll
by
put
the
it.
How
way,
does the
then couldn't we
maximum
just
Hmm? Pranav, what did you say?
or like how does the maximum denominator one has only two neighbors at max?
Yes. Uh, like the numbers it appears in between, it's a neighbor of at
Yeah.
best. Suppose there's a thing that's not a neighbor. I mean, that's not adjacent to it, but here.
Uh-huh.
Like it's not obvious. So let's prove it. Suppose we have x by n. So this to be my favorite thing to use recently. You have a by b and c by d.
what are you trying to prove?
Oh, x by n and c by d can't have cross product one.
Okay.
Do you see why this can't happen?
For that, a should be equal to x plus c upon n plus a by b should be equal to x plus c upon n plus d,
At
and
least,
then
yes. So
since
like b has to be at least n plus d in this case.
yeah, and since n is the
But we
largest
assume
number,
inverse maximum. Yeah, so that works. Oh, it's only two things
Why
at
should
a
B
time.
be at least n plus D?
A by b appears in between two things like this.
No, but like this is true only if when B like is the smallest such number. If B like x by n and a by b might also have some numbers between them.
X by n and
A by b.
between.
Mm, I mean
Okay,
we.
maybe think of it this way. I get your point. Instead of this, suppose it has two neighbors in some direction. Suppose this exists and this exists. Then these two are neighbors in the fairy sequence, and these two are also neighbors in the fairy
Oh yeah,
sequence.
got it now.
Yeah, okay, that was a valid point. So in this case, we do have b is at least n plus d, which is not possible since n is the maximum thing we pick. And so we are just done because now we remove this thing, and by the inductive hypothesis, we have at most these many pairs. So add 2 over here, we get the bound we wanted. Okay, there is an interesting geometric proof though, which is very similar actually, but I thought it's nice. It's not really relevant to fairy, but I'll just mention it. Choose the number with highest sum of coordinates, which is essentially what we did here. So this is say point P. So like we're going to label coordinate, this is going to be AI by BI, I mean AI comma BI. So also note that no coordinate can have like two non-coprime numbers as their coordinates, because then the cross product can never be 1 unless there are zeros, but that's only 1 at most. Okay, so now like this point P exists. So this condition that cross product is 1, by shoelace thing, it says that points say P1 and P2, the area of O P1, P2 is in fact exactly half this cross product, which we'll actually define by D. It will be relevant later, probably. So we're really looking for the number of pairs of points you have such that the area of O P1, P2 is equal to a half. It's like, it's actually very similar to the fairy thing. Suppose we have P3. uh, and now suppose we have a P4 here. So now these triangles, the purple one and this orange one, they have equal area. And therefore we have this line P is parallel to line. But actually remember that P1 had like irreducible coordinates and we picked it to be technically the farthest off. So this can't really happen actually. Because
Why?
uh, it's actually easy enough to prove. I'll just take an example. Suppose you have a 3 by 4, 3 comma 4 point here. So like this line has slope 4 by 3. So if you are starting at a point somewhere else and drawing a line with slope 4 by 3, because like they're co-prime, you'll need to go up at least 3 and to the right at least. I mean, you have to go up at least. Suppose this point was x comma y. Then the smallest lattice point you're going to get on this line is 3 plus x comma 4 plus y.
Got it.
Yeah,
By
but
the
that
way,
is
in the fairy sequence,
Hmm.
can't we just consider directly AI by BI instead of AI by AI plus BI?
I think you can, but there is some slight problem with 0 by 1 or 1 by 0 being there.
Why?
I think 1 by 0 is the problem.
Like we are not even looking at fractions. We are not even focusing on fractions. We are mainly focusing on this BC minus AD equal to 1 property, right?
It's like really the actually does this work?
Also, like the coordinate solution you mentioned,
Hmm.
it suffices to have P1 with like max X coordinate or max Y coordinate, right? Sum is not necessary because the only thing is that for 3 comma 4, suppose the Y coordinate should at least decrease by 4, right?
Yeah, I think the point of sum of coordinates is if you're only considering x coordinate, then I'll like pick 0 comma 1 or something.
But there can be 2 points on the same side, right? That's the key point.
Yeah, like I'm saying this is possible. Consider the point 1 comma 0 comma 1 here and consider the point 3 comma 5 here. So like this is in fact parallel. So like you in fact do have these three work and those three work. So you can't just focus on one coordinate.
Oh, okay, got it now.
That's why you focus on sum. And this is the
So,
same problem for the fairy, I think.
so for this solution to work, we somehow have to remove the zero stuff.
Yes, and that is why we do this. AI by AI plus BI.
But if we only focus on the fairy sequence, then in that where is the problem?
There is no problem. Like the fairy sequence works perfectly fine. Like
If
for
we write each as AI by BI.
yeah, like for example, you can choose 1 comma 4, 1 comma 3, 2 comma 5, 1 comma 2 and
No,
stuff.
I'm no,
It
I'm
works.
asking you in the fairy sequence solution, you choose AI upon AI plus BI. Can't we just choose AI by BI?
Yeah, I think. Okay, I'm sorry, I don't really remember this fully, but can I just like tell you after the class? I don't fully remember, but I remember like this was the first thing I tried to do too, but it failed because of zero stuff.
Okay.
And then like I found another solution, but on the thread they do mention that you can do the substitution and get rid of the zero problems. Okay, I see we're at 8:30. We will not be able to do something else I plan to do, so we'll just do another problem. This one will probably convince you fairy sequences are actually very useful. As in like, this is a very respected source. This is 2016 A5. So we're only going to solve part A, not part B, because part A uses fairy. Part B, you can't. So
Which part is fairy?
A, ignore this. And A is also the harder part. I could have cropped it, yes. Okay, while you people think about the problem, I will crop it. Okay, also for this problem, I will mention there is a nice solution without fairy too. It's like, this doesn't really count as spoiling it because I think the idea needed in that thing is
Could you
quite.
repeat? Is there a nice solution without fairy, or is there not a nice
Oh,
solution?
there is a nice solution without fairy. So this is not really spoiling the problem. You can still try the problem and try to find a nice solution. But I will say
Taking a by b as root time plus root time plus 1 by 2, why does that not work?
what?
Take the arithmetic mean of root n and root n plus.
Integer. Integer.
Ah,
Okay, anyone have any ideas? Or actually, what is the problem asking us to show? Assuming we just phrase it in terms of fairy stuff.
I cannot say fairy being used directly, but maybe that tree which you showed, like like
So
I
you
took
don't really care about the integer part, right? So like you really want a fractional part of root n less than or equal to a by b less than or equal to fractional part of root n plus 1. Because then you can add a suitable integer.
But fractional part of root of n plus 1 can be less than.
Ah, can it? Okay, so what happens, in what case is fractional part of root n plus 1 greater smaller than root n?
When n plus 1 is a perfect square.
Yeah, but if n plus 1 is perfect square, then like just pick a by b equal to that.
Okay.
So really the problem wants you to show that in a fairy sequence of order floor of root n plus 1. That's what this says. You can find a number which is between root n and root n plus 1. Which two neighbor elements are you picking? Okay, yes, first. As you said, let x be the floor of root n. So this is x plus 1. I didn't really get what you meant by pick two neighbor elements. Like there are many, which one do you want to pick? We are trying to show that A by B exists. So what do you mean by pick one of them is A by B? Okay, so suppose there is no A by B such that this is true. Then we can find an A by B here. I won't mix up variables. C by D less than this and an E by F less than this. Such that C by D and E by F are fairy neighbors. So how do you think we could use the fact that this interval contains this big of a range? Because this is somewhat big relatively.
Could you repeat?
Essentially like this range has length 1 by df,
Yeah,
and that contains like two things which are a bit far apart. How do we use this?
we consider their difference.
Exactly. So we have that uh, fractional part of root n plus 1 minus fractional part of root n is less than or equal to strictly less than 1 by df. And I'll just write this. This is root n plus 1 minus root n. They're the same thing. Okay, also first of all, df, we need to like be able to say something about df, right?
Yeah, we can see that d plus f is less greater than x plus 1.
Yes, exactly. and therefore this is.
How do we get that?
Arjun, you want to explain?
Like c plus c upon d plus f is also between them, and if it is not in f of x plus 1, it means that d plus f is more than x plus 1.
What's the how? Ah, okay, okay.
So we do have some kind of bound on df. So really, you want to bound this value in
Yeah,
terms.
you can use AMGM maybe.
What does AMGM say?
DF is like root DF is. I mean, should I repeat the statement or?
No, no, don't repeat. I know, yeah. Like I'm sure most people know AMGM, but like AMGM isn't really helpful, right? You want what do you, an upper bound, a lower bound on the product in this case. For example, like this product is actually maximized at 1 and x, or 1 and x plus 1, whatever. I mean minimized.
Could you repeat?
Like we want to show this is less than something, right? So you want df to be greater than something.
Oh
AMGM
yeah.
is the ulta.
So maybe we can bound 1 by x or
1 by x?
like 1 by df is less than equal to 1 by x.
Less than 1 by x plus 1, yeah.
Oh yeah.
Yeah, in this case, that will actually not be strong enough. So
I
actually,
think we can
what
achieve
is
1 by
strong?
x only
How?
because
This is greater than, not equal.
because x is not an integer, right?
Oh, x is the floor.
Oh, okay.
Okay, so really, if we want to know what bound is strong enough on df, you want to bound root n plus 1 minus root n in terms of x.
So maybe write root n plus 1 minus root n as 1 upon root n plus root of n plus 1.
Exactly. I'm assuming most people see why this is true, just cross multiply. And
And
what does this give?
1 by 2x.
2x?
2x.
Yeah, fine. Talking about 2x plus 1. But fine, yeah. This will, yes, this is actually good enough. Yeah, wait, I actually think you do get 2x plus 1. Because, like, if you're considering the worst case for this minimum, it could be 2x plus 1.
But like we are not. I didn't get you still.
Or, like, we want 2x greater than or equal to this. That's not true, right?
But it's fraction, so
No, I'm saying this inequality is not true. Because we have, like, this x is the floor, not the ceiling.
oh yeah, sorry.
So, like, yeah, this will be 2x plus 2. It's an easy fix. So we have that what df is strictly less than 2x plus 2, but d plus f greater than x plus 1.
Oh, so one of df must be 1.
Hmm?
Oh,
2 works, I think.
oh yeah.
Yeah, either one of them is 1 or one of them is 2. So let's say d is 1, then you want, basically the point is there are finitely many such cases, and in fact you can check all of them just fail by just checking this.
What do you mean by finitely such cases? Like
Oh, there are, like, if d is 1, then like if d is 1, then like this is actually easy to see this can't happen, right? Like d can't be 1, or I mean, okay, in this case it's probably f that could be 1.
why can't d be 1?
Like this is less than 1, this fraction, so this would be 0 or something.
Oh,
Like basically the point is if d equal to 1, fine, there is, I mean if f equal to 1, there are some cases. But if d is 2, then f must be x or x plus. In fact, it can only be x, right? Because anything else would violate this inequality. Because then this would become like 2x plus 2, which is not possible. So you can just check that in these cases it works out. Like I've already exceeded the time by quite a bit. So I'll actually just leave this as an exercise. And it's also in the problem set. Like, you can try it. And also part to be. It's nice. Okay, so unfortunately I was not able to finish everything I wanted. But fine. I guess that's it.
Awesome, man. Thank you so much. That was an amazing session. I mean, I don't know why you were nervous, but that was
Very.
awesome. Yeah. Oh, by the way, guys, I keep forgetting to say this, but fill out the feedback form. I'll post later. But yeah, that was an awesome session. I have no clue why you were so nervous. Oh, wait. Recording.